Okay, hello everyone. This is basically the second part of Wednesday lecture, where we, as promised, we're going to go through a review of or solving of heat transfer or thermal system problems using ANSYS. And again, the reason for this is the our inability to access ANSYS on in the lab, and which is I think is solved out now. So we are good to go. So I just want to go quickly through the theory, and again, you guys, some of you are working on thermofluids, so they are more experienced in this, and they can always, interject and provide more information when needed. So basically, when we talk about thermal analysis, we're talking about steady state, or we're talking about transient, or we're talking about thermal stress analysis, right? And basically, we have discussed this briefly in class. So. Steady state is basically, basic definition is independent of time. Transient is a function of time. You want to see the history of how the temperature profile develop or advance with time or change with time. And then thermal stresses is if you have a constrained body that is subjected to a heat source, and metals and other materials basically stretch or shrink due to variation in temperature. And if there is no way for it to stretch or to shrink basically due to constraints, is going to develop internal stresses or thermal stresses. So we want to see how we can do this analysis in ANSYS. So again, you guys again are familiar with heat transfer. So this is the heat conduction equation, K, and this is the variation of the temperature with respect to X. Of course, time here is not considered as a state. And F represents the heat flux, so very similar to the formulation of finite element that we did before, but K here has a different definition. It has to do with the conductivity, right? And again, this is a formulation that you can read through the book, but I mean, the idea again here, this should remind you of the general finite element equation mx double dot plus cx dot plus kx equals to r. In this case, basically K is the conduction or the heat transfer coefficient. This is the temperature, variation in temperature, and this is Q, which is the heat flux, which represents the external force. Right? So basically for a steady state, which is this formulation here, time is not taken into account, so the temperature assumed not to vary with time. When you go to transient analysis, basically the derivative of temperature with respect to time does not equal zero, right? Temperature varies with time, right? And then the third thing is the thermal stress analysis. And again, thermal stress analysis, we all know the basically the equation for stress, which is basically sigma is equal to E modulus of the system multiplied by the strain. This is the general one, but then again, due to the temperature variation of the heat source, we have stress that developed due to the temperature. So variation in temperature multiplied by a coefficient of thermal expansion. In this case, our epsilon is going to have two components. One of them is the elastic strain or strain due to mechanical loading, and the other one is due to thermal loading. So basically, the strain is equal to sigma divided by E. From Hooke's law, sigma is equal to E epsilon, and then the thermal one is equal to alpha delta T, right? So basically, we can here write that sigma, if we take this equation amplified, sigma is equal to E, and then the variation of the thermal stress, right? This is the equation, right? And these are examples again available in your textbook, just theoretical examples showing you the calculation when the strain basically change. And of course, you know what is Poisson ratio. So basically, Poisson ratio determine the relation between the strain in two different axes or two different axes in the transverse and lateral direction, so an X and Y direction. So if there is a change in the strain or there's a deformation in the X direction, it is related to the deformation in the Y direction with the Poisson ratio. Usually for metal, the Poisson ratio is around 0.3. Okay, so with that, I just, again, this is, as I mentioned, assumed to be part of your knowledge, prior knowledge to the course. We are not teaching really heat transfer, but trying to understand how does ANSYS can do this. And with that, we are going to basically, we know the modes of heat transfer, again, conduction, convection, radiation. And we are going to, what we want to do, we want to solve this problem, thermal analysis. So this is basically a heat sink. And we want to model this in ANSYS steady state, transient, and then, what do you call it, sorry, and then thermal stresses. And this is basically the problem definition. So I leave this for a minute for you to watch, and then we can go and start ANSYS and start solving this problem. So this is the information, part A, part B, part C, which is the steady state, transient, and thermal stresses. And this is the details of the material properties. Aluminum, if I remember, I mentioned we are going to solve the aluminum. This is the boundary conditions and the initial condition for the steady state and for the transient. And this is the geometry that we need to generate. So going back here, so you take some time to read. So we are going to go to here to select thermal. Okay, thermal steady state. Where is thermal steady state? Should have it here. Steady state thermal. Double click, and then, as we know now, you can type this. This is heat sink. Okay. And of course, as I told you, you always need to save. So I'm going to save here, and I'm going to save this in my lecture folder. So when you guys, when we start in the class, I can bring it back. So I'm going to go to fall 2022, this one here, and I'm going to engineering, okay, workbench, heat sink analysis. Okay, so as we mentioned, we have to go through these steps, and I want all you to remind, whenever you go through this, remember the 7 golden rules that I've shared with you for solving any finite element problem. Discretization, nodes and element, which is basically nodes and elements, element equation, then stiffness matrix, boundary conditions, and then solution for the nodal analysis, for the nodal solution, and then for the other calculations. So in our case here, we are going to select a different material, right? So in our case, you can basically add a material, or you can select from the materials that are here, right? So basically, we should have a database for different materials, and we can select from it, right? So different kind of materials. So if I go back here, sorry. Okay, no, okay. So we want to define a new material. So, okay, what happened here? Okay, something is wrong here. For some reason, the menu is not okay. I don't have to delete this, but I can add a new material. Fluid materials. No, I don't want this. Okay, let me double click and go back again. It's always good to learn these things. But I should be able to add a new material, which is, for some reason, it's not coming. This is, click to add a new material. Sorry, it was not, for some reason, it was not sized enough. So I'm going to call aluminum, okay? So in this case, of course, aluminum is a material that is available in the library, but I think what the The example here is basically has a special grade of aluminum that is basically that has different material properties, right? So we have to go to isotropic. When you click on isotropic, you know different materials here. Your isotropic thermal conductivity, the value here, and I have to remind you in this example to please be aware of the units, right? So 170. So this is the material. Of course, you know that many mechanical properties vary with temperature, and so they are not really a constant. So ANSYS has the capability allow you to enter a function. As you can see here in the graph, this is just fixed value for the thermal conductivity key, but you can enter for example, an Excel sheet that basically varies the mechanical properties or whatever property with temperature, right? So you can do that, but again, hopefully you'll be able to explore some of this stuff in your projects. Okay, so in our case here, again 170, and the units are given watts, meters, watts divided by meters per degree centigrade. So we are good. We go back to our project. You can close this or keep it, and then we go to now to create the geometry. So again, as I mentioned, you can always go to geometry, you can import it, or you can basically use the space claim or the design modeler. New discovery is, it seems to be something new with ANSYS 2022 that I am not familiar with, so I'm not going to touch upon now. So we are going to use space claim because this is again the one that is your textbook adopt, but not necessarily. But I think the general understanding is space claim is more advanced or have more capabilities than the other one, which is the design model. Okay, so if we go here, we need to basically again space claim will open. We can always go select this one, select this plane, and then go to plane view. But before doing this or after doing this, we have to go to the units and make sure we are using the proper system of units. So in my case of units, I'm going to use millimeters. That's what I want. And I'm going to basically set the precision here to basically certain value. So I can primary angular precision. And if I scroll down, I'm going to keep this at 1 millimeter because the units I'm using for the object is very small. So this is good. I'll just bring this up to remind you. So basically what we're going to do, you guys are good in solid modeler. We take a cross section, which is this one, and then we extrude it. And this will create the 3D model of the problem, right? So what we need to do is basically to create this. And to create this, you can again create the whole thing or create only one part and basically about the y-axis and then use the symmetry to do mirroring. Both options are good, depends on how complex, and I'm sure you have many ways to create this. So I just want to remind you of that. Okay, so we are good now. We need to start creating this shape. So basically lines. Okay. Go. Okay, I have to zoom a bit, I guess, so I can see things. So this line is 11, as you remember. If you don't trust me, you can always go back. 11, and then 3, right? And then you can do the calculations. So this is 1, 1, 1, that's 4, and 4 are 8. So this distance is 3. And then I have to go up 8. Okay, so I have to zoom back here. 8, 8, 8. Okay, click. And then I have to zoom in. Oh, it's not coming. Okay. Then 1. And then go down. And then 2. And then go up, 1, down, 2, and then 1, 1, down, and then 1. Oops, no, that's wrong. Okay, so I need to delete this. So select, delete. Okay, no problem, that's fine. Select using box. Okay, I'm going to this, and then you're going to delete. Okay, that's okay. Okay, I want to delete this line here. Okay, it's not selecting. Okay, it seems I'm not really an expert at this, but that's good. Using box. Okay. And delete. Okay, so back to where we are here. So line again. That's good. From here down to here. And up to here. And then right. So basically we have our object. We can go back to home. Sorry. Yeah. Plane view. I just want to make sure that I have a line here. So how many lines do we have? Yep. Sketch 1, 2, 3, 4, 5. You can count the lines. Okay, so good. We are very good now in a good position. So now what we need to do is basically we need to use the mirror option. So to use the mirror option, I need to go to design here, and there's an option for mirror. Where it is, mirror. Okay, select mirroring plane, which is this plane. Everything. Sorry, I was calling somebody here, so I do apologize for that. Okay, so let's do mirror again. Where are we? Mirror. Select mirror plane. This one, and then select objects. So we can using box. So we can select the whole thing. Click on the select and chain, double clicking. It didn't work. Feeler. Okay, again. Sketch, design, mirror. Select the mirror plane, which is the Y plane. Okay, select the body to mirror. Select the body to mirror. I am going to select this. Yeah, and that's it. If you click on it, it's going to select all of it. So we're good. Right. So we have the mirror. That's good. Lines. Excellent. Now we click on the y-axis and then click on this. Now we need to do the pull like we did before. If you remember, we had a struggle with that one before. So basically, I need to know what was the depth of that thing. Okay. So now we go to here. We are done. If I go to display, no sketch, and then pull. And pull, basically you select this, and of course you can rotate it to see it in 3D or in isotropic or whatever whole position. So you can basically start moving this way. So of course what you need to do is we need 15, so you can keep moving until you reach 15, or basically like this, and then enter. We're good. Okay, extrusion products. Okay. There is a problem here, right? So let's see what is the problem. So solid, and I think this is more than 50, and I'm going to tell you why in a minute. Okay, but let's there be a way to do it. So when you do extrusion, right, you can do extrusion basically if you are on the XY plane as we are. Okay, you can ask the extrusion to be in the positive Z, in the negative Z, or you ask the extrusion to be around the zero. So if you want 15, it could be 15 from 0 to 15, or it could be from 0 to minus 15, or it could be from minus 7.5 to 7.5. You can do a lot of control in the extrusion module here when you see the options for extrusion. But for now, I'm going to assume this is to be 15, which is, I think it is not, but you guys need to believe me. And basically we will take it from there just for sake of time. But of course you have full control over everything, right? In terms of how you extrude and all the stuff you can always do. So this is basically you can always see different views of things, and you can always go and see the isometric, which is very good. So you can always go back. So for example, if you don't want this, and you can always go back like this, and then you can do the extrusion again. So if you go to the pull command, and basically you select this, and then here you see these are the options that we pull both sides, pull thicken surface. You can pull in one direction, you can measure, you can do a lot of things, and some of these we are going to experiment with when we do this. So I think here for some reason it is no, yeah, that's now not pulling in one. You can see this is pulling in one side. So I'm going to accept this, and then we are going to press enter, and this is basically or escape, and then we have our object now, right? So I think this is now 15 because the coordinate system is here, so we are good, right? Okay, so anyway, we can play with this for many times, but now we want to move ahead. So we are going now to, we're done geometry, you see the tick here, now the correct, so we go now to the model. Okay, so let me do one thing. Let me, until it loads. So we have our model with the geometry. Now we need to start applying the load, of course, the mesh, the load, and the boundary conditions, and we want to see what kind of information we want to see. So let me go back here. These are the boundary conditions for a steady state and the initial conditions for a steady state, and this is the information that we need. Of course, some of you might ask, we didn't enter all these properties, we just entered this. And the reason for that, I think, is you need only this now for a steady state, but we'll always go and update the information. So that's what we'll be doing. Okay, so modeling. We go to modeling, and one of the things that I will always remind you to do is the following. Units, right? And we can, it's millimeters, newtons, millivolts, so that's okay. Now we go to generate the mesh, and in the mesh here we can go, and of course this is statistics. I told you about different techniques for meshing before, but you can test others as you move on. So you see here, this is a coarse mesh. We can change that to a fine or medium mesh. This is one way. And if you go to that, basically you're going to find that the minimum edge length is 1. So let's mesh with that, and let us see what we are going to get. So this is our mesh, right? You can basically change it if you don't like it. This is basically 1000 element. You can go and element size. You can make it, for example, 0.5. Okay, millimeters, of course. That will basically double. You can see here, and then you can see update mesh, right? So it's going to change from 1000 elements to, wow, 13,000 elements, right? Because 0.5, remember 0.5 erasure. So that's, I'm not sure how we are going to solve with this, but let's see if the system is going to take it. This is a student version, so I'm not really sure. But anyway, let's see what we can get. Now, we need to apply boundary conditions, and we need to apply the loading for this problem. So we are going to go to steady state thermal, and under steady state thermal, basically we want to apply heat flux. This is a heat sink, so basically the base is connected to the motherboard of a computer or processor where heat goes in. So we're going to go insert, and we are going to basically select heat flux, right? So heat flux, you have to select the geometry. So you go to the tools here, as you guys expert, and you select this face. And what is the value of heat flux? Okay, so because our units are millimeters, we have to change, right? So if you go to the heat flux value given in the question, heat flux is 1000 watts per meter square. So basically you need to convert it, and here it is basically 1000 watts per meter square. You have to convert it, and I did the mistake earlier, and I thought it's watts per meter square. If I want to convert it into millimeter square, I multiply it by 10 to the 6, which is wrong. You have to divide by 10 to the 6, right? Because this is basically millimeters. Meters, so basically you want to change meters to millimeters. So basically 1 meter in the numerator, 1 meter is equal to 1000 millimeters. So the 10 to the 6 is at the is here. So this is basically converted to millimeter. So millimeter is 1000 meters squared. So it will be 10 to the 6. So you're dividing by 10 to the 6. When it goes up, it's going to be 10 to the minus 6 multiplied by 1000. So it is basically 1. The first time I did it 1000 multiplied by 10 to the 6, and then the software told me, no way you're getting to get an answer for this. It gave me a major error. I was planning for doing this in class, that you guys go through this error with me, but you're lucky. So we're going to make it like this, right? And then, of course, you go selection here and apply, right? So you can see here, we're applying a heat source at the bottom, right? Excellent. What else do we need to apply? So, sorry, heat flux, which is a heat source. Yes, I'm just using different. Okay, now convection from everywhere. And again, convection here is going to be from everywhere except for the from the base, right? Because the heat comes from the base and goes from all the cells. So basically, again, we go here, we insert convection, and convection is going to ask me to select service. So I'm going to select everything. So basically, there are different ways of doing this. So I am going to select all. And then if you go like this, and I think you click on the control button, we can exclude one. Go and click on the service, because we don't want convection to be, so right? So basically, again, we did that. So we selected everything except for the button. So we select all and then click on the control button, and you can remove the services that you don't want. The ambient temperature is 28 according to our problem. No clue why, but that's what it is. And then this one again, we have to convert into millimeters. So it is 30 watts per meter squared using grade. So it's going to be 30 e to the minus 6 to convert the millimeters to meters, right? Because the units here are millimeters. And then of course I have to select apply. So you can see here heat flux is applied everywhere except at the bottom. All of things is yellow except for the bottom. What else do I need to do? Okay, now we need to go to solution, right? So in solution, we need to insert, what do we want? I want to see the temperature, of course. Everybody wants to see the temperature, right? Total heat flux, directional heat flux, right? You can see whatever, all directional heat flux. So directional in which direction? I think it should be in the y direction, if I'm not mistaken. So we can change that, or x, or z, or whatever. So x, y is going up, so let's do that. What else? You can see a lot of things that we're going to discover as we move on. But for now, I think this is what we want to see. Now, all we have to do is just to solve. I wanted to say something, but I forgot what it is. Okay, yeah. So again, when you remember the 7 rules for finite element that I shared with you in the lecture, basically in software packages, basically you divide them into pre-processing, which is basically creating the model and creating the mesh, and then processing, which is basically adding the loads and the boundary condition, and then solution. So these 7 basically fall under these three categories. Okay, so finger crossed, solve. And let's see what we are going to get. So solution is done, great. We can see the temperatures. Of course, the temperature goes from the bottom to the top. But you don't see that much variation in the temperature, by the way, right? At the top it is 33, at the next one there isn't much heat, so something wrong with our, I think, convection. This is the heat flux, and this is the directional heat flux in the line, right? So, of course, if you don't like the results, you can always, go and review your solution if the result doesn't make sense. However, it does actually make sense in this case, right? Because we didn't have much heat going on from the bottom, right? Or the heat flux was not that big. You can always go and say, okay, let's do a bigger heat flux. So instead of 1, we're going to make it, it was 1,000 e to the 6. I'll make it, 100,000 e to the minus 6. Sorry, to the minus 6. Okay. So it is 0.1 watt per meter. Let me even make it 0.5. Give okay, solve, right? And we can do that. So let's see what's going on. Okay, so we look to the solution now. You see, no, the solution now, the temperature is what? 2,750 as compared to 33 before, right? So you can always, this is the beauty, right? Solving the computer, you can always test different things. So in my case here, I'm going to make it 1, just bring it back to what it was before, and then I'm going to solve. Of course, you can change also the convection boundary condition and see how it affects everything, the coefficient, or you can change the material. If you go back to material here, you will see that what we have is our aluminum, of course, right? Isotropic. I think we did a mistake here. Isotropic 0.17. Okay, geometry. Aha, properties. Okay, I think I forgot to do something here, so let me see if it is or I did it. Okay. Imports. Okay. Okay. Okay, I think what we have done here is the following. Okay. Yeah, one of the things that I wanted to actually show you, you go to here in Geometry System Solid, and you will see here that the assignment is structural steel, which is not true. Our assignment is aluminum, right? So our material is aluminum, right? So we have basically to resolve again. You can change if you go to this one, because we did not assign the material in the space claim. So basically you need to do aluminum here, right? Assignment is aluminum. And you can always change the material. So if we did for structural steel and then you want to do for aluminum, you can do it. So if we change it to aluminum, you see here everything's changed now because we have changed some of the initial parameters. So I have to basically resolve again, right? So I'm not trying to follow the steps. I'm just trying to think and look and try to figure out, just to show you that, sometimes you make mistakes and it's easy to change, right? The temperature is still pretty much the same because we use the same boundary condition, so there isn't really much of a difference. But that's what it is, okay? And of course, you can show the colors to somebody who doesn't know, and they think you're basically doing magic. So I hope this is clear, and I appreciate if you can solve this and save the file so somewhere accessible, so we can continue from this file when we do the work on Wednesday, sorry, next lecture, and we basically continue with the transient and with the thermal analysis. Okay. So you can see the values here have changed, direction of flux, and you can always, simulate things and see how it goes. Okay. I hope you find this useful, and please practice on this, and we'll see you next time. Thank you.